Hello students, you all are warmly welcome to our YouTube channel Chemistry Teacher. Here, we are going to present you another lesson regarding isomerism that we find in our organic chemistry. Students, so far we have talked about isomerism. Hope you know very well what is isomerism. What is isomerism? Students, it's the having of different compounds, the possibility of existence of different compounds representing the same molecular formula. That's what we call isomerism. So we call having of different structures for the same molecular formula. That incident is the isomerism. Then this could be or this could reach in different ways, as sometimes the same molecular formula could have different structural formula. So we call them structural isomerism. We talked about structural isomerism. Again, we could have different compounds, different structures for the same molecular formula, but having different structural formulae. Then we call them structural isomerism or constitutional isomerism. So there are three types within that structural isomerism you found. Changing the chain, main carbon chain, it was the chain isomerism, and changing the position on the main carbon chain of those alkyl groups or subfunctional groups or functional group, the functional group, as well as it could happen changing the type of the functional group. So we call them respectively. We call them chain isomerism, position isomerism, and functional group isomerism. Then students, if possible, another different type of isomers you to find out, they would have the same structural formula as well. For the same molecular formula, when they have the same structural formula in the way they arrange in three-dimensional space, let's call that the spatial arrangement. Regarding their arrangement in the space, where they have got arranged, they are different. For the same molecular formula as well as structural formula, you get different compounds having their arrangements of those groups or those atoms differently in the three-dimensional space, spatial arrangement. So we call them stereoisomerism, or we call that stereoisomerism. So those are the stereoisomers when you get such. Students, this could reach in two ways. Yes. It's we found that out. The first way was the optical isomerism. It was in our earlier topic. So we talked about the optical isomerism, that when you have got one carbon being surrounded by four different groups, atoms, then their arrangement in the 3D space could be two different. One is the mirror image of other. They would arrange tetrahedrally. So then they would arrange differently. So we call them optical isomers for the reason you could distinguish them in a physical meaning only. Means it's passing monochromatic plane polarized light. You could find one is changing its direction in one hand, it rotates in one hand, the other is in the opposite direction. So accordingly we name them as LD. L means left or levo in Latin for left is L. So other words, D, dextro for right in Latin. Okay, so anyway we have talked about them. So let's come to the point. Here we are going to talk about the geometric isomerism. It's the second type that you meet under this stereoisomerism. Okay, so it's carrying the same molecular formula as well as same structural formula. Still, it's possible then to have two different compounds structures arranging differently in the 3D space in this kind of way. What's the way here? Students, let me first briefly introduce you the thing that when you have a carbon-carbon single bond, then it's through this bond axis. These two atoms could rotate. Therefore, if you have got different groups here, let's say, if you have got different groups here, their spatial arrangement you can't talk differently. For the reason they could rotate through the bond axis, around the axis they could rotate, and once when they locate in a way, they arrange in a way, it's at the next time they could get rotated and arranged in a totally different way. Therefore, if the same molecule could arrange differently, then it's not having a chance for two different compounds. It's the same compound. It's the same compound you get differently arranged based on the situation, based on the environment, based on the time. So therefore, students, we call that free rotation. When you have a carbon-carbon single bond around the bond axis, those two atoms could rotate freely. Therefore, there is no chance, it leaves us no chance to talk about two different compounds. It's if I start trying changing the place of B to A, saying that it's a different compound you get. But it's once when you do this compound, same compound could take a rotation there as to at the next time as to reach that other position what I have thought about as a different compound. Same compound could reach those different arrangements, different spatial arrangements. Therefore, students, it's when you have a carbon-carbon single bond, there's a rotation, free rotation possible around the bond axis. Therefore, we can't talk about different arrangements, comparatively different arrangements in 3D space regarding those groups. Okay. Then what about this isomerism? What have we got here? Students, it's not when you have a carbon-carbon single bond. A carbon-carbon single bond having that, it could rotate around the bond axis. But when you have a carbon-carbon double bond, what does it happen? When you have a carbon-carbon double bond, one is sigma, overlap linearly, other one is a pi bond. So it's a lateral overlapping. So when you have such a carbon-carbon double bond, it would not be able to rotate around this bond axis. The free rotation is blocked. We call it the free rotation is hindered. It's the hindering of free rotation. Free rotation is being blocked. It has been hindered. So that's our first requirement, to talk about this kind of having different compounds, this kind of isomerism. It's first you need to have a carbon-carbon double bond hindering the free rotation around that bond axis, right? It's normal you could talk about a rotation. Then students, it's when you have a carbon-carbon double bond, other two could be a single bond. Then only we could talk about two different groups. We could place two different groups or atoms here. So here also you would have another two bonds. So then if we are talking about such a situation, when you have a double bond hindering the free rotation around the bond axis, and then it's the second requirement on each carbon. On this carbon, let's talk. On this carbon, if you have two different groups, it's A and B. On this carbon also, if you have two different groups, it's again A and B. If they are not supposed to be the same, means it's not a mask. This If this is A, this shouldn't, it's not a must to be A. It's not a must to be A. Anyway, in my example, I have taken it in that manner. So, when you have a carbon-carbon double bond hindering the free rotation, and on each carbon, when you have two different groups, then students, it's you are having a chance to get two different compounds. As one is this, the other one is when you have the same A and B here, and when you have these positions of those exchanging, as here now it's not A, now it's B, and this is A. So these are actually, when you consider their geometry, it's you find it's a trigonal planar geometry the carbon is having. So then in this geometry, you could change the position of those, then get a different compound. These two are different compounds. But students, when you check for their structural formula, this is actually the geometry what I have drawn. When you check for their structural formula, it's on one carbon you are having A and B. It's not giving us the sense that how is that those two were arranged. So then it is here also A and B. This is not remaining, it's this or this. This is just the structural formula only. For this structural formula, the molecular formula is CAB and CAB. So then C to C there is a bond. So that's the molecular formula. It's actually we denote molecular formula with number of carbons. So this is still the structural formula. It's C2, A2, B2. That's the molecular formula. This is actually not. This is just showing that you have carbon, they have got attached each other. So molecular formula explains only about the number of those atoms. Students, this is the molecular formula. For this molecular formula, it could have this structural formula, but this structural formula could carry two different structures. One is this, the other one is this. Okay students, now the matter is how could we name those two different structures? It's called isomers, those geometric isomers. How could we name them? Okay, so when you have such two isomers, if you find, let me erase this now. If you find that two similar groups facing each other, this is the bond axis. So at the same side of the bond axis, if you find they are facing each other, then we could call them cis. It's in Latin at the same side. Cis. So it's the cis type. It's we call cis-isomers. Cis type. Not cis type, cis type. Then when you find it's on these two carbons, you find the same group A. But when you compare their location, when you consider their location through this around this bond axis, it's not the same side. So it's at the other side, means through where it has gone through. So then it is through in Latin is trans. We call that trans type. So we get cis isomer and trans isomer. That's how we could simply name them. Now we are going to find out some examples standing for this type of isomerism. Let's consider butene. So it's 2-butene also you could call that. When you have 1, 2, 3, 4 and the double bond here, it is either 2-butene or butene, the name. This is the what? Structural formula standing for but2e, 2but. Students, you could find this 2but carrying two structures existing as two compounds. So this is the carbon-carbon double bond. So geometry is trigonal plane and trigonal plane. So here also is the same, but when you check for the position, here you have a methyl group and hydrogen. Methyl group and hydrogen. So it's methyl group and hydrogen, right? And it's now they have exchanged. So it's hydrogen and methyl group. Okay. Those are the two possible different compounds being arranged differently in three-dimensional space. So this type is having methyl facing each other. So this is the cis 2butene or but2e. So students, I need to make a correction regarding their names. If in the nomenclature I have earlier mentioned that it's okay leaving the first letter capital as well. But students, now it is strongly accepted, recommended writing all the letters simple only. It's in the marking schemes, A-level marking schemes, you will find those answers not being marked when you write the first letter capital. So when you name it, when you give the nomenclature of those organic compounds, you make that sure writing all the letters simple. Okay, students, then it's cis but2e or cis 2butene. Cis 2butene. Here the name. So this one is the trans 2butene or but2e. So in that manner, you could name them in the form as cis-trans. So let's find out some other examples as well. Students, when you have a structural formula like this, it is a carbon-carbon double bond, it is a hydrogen-chlorine, hydrogen. Then it's not satisfying our requirements, basic requirements. What are the basic? So first you need to have a carbon-carbon double bond hindering the free rotation. Yeah, we have that here. Then on each carbon you need to have two different groups. Here you have two different groups. It's hydrogen and chlorine atoms. Here you don't. It's the same hydrogen atom. Therefore, this is not exhibiting any such geometric isomerism. Then students, it's when you take, let's not draw it three-dimensional way. So it's just the Lewis structure. When you take chlorine, hydrogen, chlorine, this could exist in two ways. Like it's having those geometric isomers. So then it exhibits geometric isomerization around this two carbon with a double bond. It's chlorine, hydrogen is the cis 1, 2 dichloroethene. So then the other type is chlorine, hydrogen, chlorine. They are not facing, these chlorines are at opposite side. So it's trans again same 1, 2 dichloro ethene. The name of that. So let's find out another different example. when you have something like this, you have CH3, you have a H here, you have CH3, you have CH2, CH3. Then it's satisfying our needs. Our needs are the having of a carbon-carbon double bond. So you have that hindering the free rotation and having two different groups on each carbon. Okay, so therefore it's you could expect geometric isomerism being exhibited. So students, let's take methyl and hydrogen, methyl and ethyl. So it's okay if you denote this by C2H5. But after ethyl, propyl butyl pentyl, you shouldn't do that. Okay. So then you need to give them as the normal carbon chain. So students, it's still methyl, hydrogen, and now ethyl here CH2, CH3, and it's methyl, CH3. So these are the two isomers. This is the cis, because methyl are facing at the same side each other. They are confronting each. So here you have methyl at two sides. So it's trans. It's the trans species. Trans. Okay, in that manner you would find cis-trans, those two types of geometric isomers. Then you might be wondering, what would it be when there are four different groups around this carbon-carbon double bond? On each carbon, if you find two different, and on the other carbon, if you find totally another two different, not being the same as of this, then also you have such isomers, because all needs, all requirements are satisfied. Then only matter is how we could name those. Let me show you that as well. So students, in that aspect, we can't use the word cis and trans. Let's say it is you have hydrogen, chlorine, bromine and iodine. This is just the structural formula only. So it's you have those requirements, those needs being satisfied. Needs are you need to have a carbon-carbon double bond hindering the free rotation. Yes, you have. On each carbon you need to have two different groups. Yes, you have two different. Now the matter is you can't name them as cis-trans. Those two structures. This is the carbon-carbon double bond. So geometry, it's hydrogen, chlorine. It's hydrogen, chlorine. But here bromine, iodine. Here iodine, bromine. There are two different structures. You could easily recognize. But how could you name them? Could you name them as cis-trans? No, the answer is not. Cis is at the same side you find confronting those same groups. Then trans is through. Through means it's through the bond axis. At the other side you find that. These cis and trans are just two Latin words standing for same side, and it's through at the other side, opposite side. Then let's use another language, not Latin, to denote that it's the same side and opposite side. But based on what? Based on what we call them, they are at the same side and they are at the opposite side. Students, let's use those atoms, the groups, these atoms, mass. Let's use their mass, relative atomic mass, and let's compare the relative atomic masses. So you don't need to know what's the exact relative atomic mass. You just need to have just a comparative idea whether its relative atomic mass is larger or smaller. So let me denote this. When you compare these two atoms, hydrogen and chlorine, which one is the one carrying larger relative atomic mass? It's this one. It's chlorine. It is the larger one in relative atomic mass. This is the smaller one. Then when you compare bromine and iodine, you could find them those in the 17th group. Down the group, their masses get increased. Then it's after bromine only you get this iodine. Then students, bromine is small, iodine is large in their masses. So it is small, large. Here, small, large, large, small. Okay, when in your comparison, when you find those masses of those groups, two groups, then comparing their masses, if you find the small are facing and large are facing. So if they are at the same side, it's now we can't use the word cis and trans. Cis standing for same group at the same side facing each other. Now also it's facing, but it's small in mass. Small groups are facing and large groups are facing each other. Then let's use German. In German, for same side, we get zusammen. It's zusammen. Students, it's zusammen. So let's denote it as Z type. Is the Z type. Then it's in German when it says through this bond axis, it's through. We call it entgegen. So we denote it by, we are not supposed to say zusammen or entgegen. We denote it by E type and it's Z type. Is the way we denote them. We identify them based on their masses. So if you find smaller groups confronting or large groups confronting, then we call them Z type. With the idea is at the same side in German. So it's when you find them not facing each other but going through, it's entgegen. So E type and Z type. This is E type. Okay students, that's how you could name them differently. They are also, you are having this. What? It's the geometric isomerism. They have two different structures, compounds standing for same molecular formula as well as same structural formula. That's the concept. That's the idea of geometric isomerism. So students, we are going to finish this theory part of isomerism. So we have talked about all those types possible under isomerism. You find its isomerism is the having of different structures, different compounds representing the same molecular formula. We found different structures being having there. For different structural formula, having different structural formula, through having different structural formula. But sometimes they have the same structural formula as well, but their spatial arrangement were different. So we accordingly named as structural isomerism, three-dimensional isomerism, or constitutional isomerism, stereoisomerism. When you talk about different structural formula, you could reach that through changing of the main carbon chain is the chain isomerism, or changing of the position of functional groups, it's the functional groups or alkyl groups or such, it's the position isomerism. changing of the functional group. It's the functional group isomerism. Then you experience that you could reach this stereoisomerism as changing the spatial arrangement when it is 4 different groups arranged around one carbon. It's asymmetrically. So they were the mirror images, one of other. So then we call them optical isomerizing. Then the other type is this is the what? It's the geometrical isomerizing. It's the geometrical isomerizing. Or we call them diastereomers. So you could name that as diastereomerism as well. So these isomers are called diastereomers, with the idea that they are not the mirror images of each other. One is not the mirror image of other. Therefore, they are called the diastereomers, with the term diastereomers. Okay, students, that what we have got within this lesson, what's the lesson? Is the isomerism. So in our next lesson, next video, we are going to talk about some examples of this application of this isomerism. How could we draw isomeric structures? It's what we are planning to do in our next lesson. Okay students, we are going to round up here. So hope you could understand these easy simple things. If you have any problem, you could mention that there within the comment box. Okay students, goodbye.